Hi everyone, my name is Ali Ayub, and today I'll be presenting our paper, How Do Human Users Teach a Continual Learning Robot in Repeated Interactions? So for autonomous robots that assist us in our daily environments, one of the key characteristics that they must possess is to be personalized to our preferences. However, over the long term, our needs, our preferences, and our environments can continue to change over time. So a natural way to deal with this is through continual learning. That is to develop robots that can continue to learn the changes in their environments and their users' preferences and their needs. Now, as one of the first tasks for the robot to understand its environment is to do object recognition, most continual learning research in the past has focused on continual object recognition. Although there has been significant research in continual learning in the past 5 years, all of this research has been robot focused, which means to develop machine learning models of continual learning that were either tested on static object datasets or on real robots interacting with their experimenters and not real users. So in this paper, we take a human-centered view of continual learning. Particularly, we develop a long-term human-robot interaction study to understand how human users interact with and teach continual learning robots over repeated interactions. So in our study, we had 40 participants that interacted with a fetch mobile manipulator robot in a tabletop environment. And users taught 25 objects to the robot over 5 sessions. So each user taught 5 objects per session. Participants were allowed to teach the robot in each session, and then they could test the robot to find all the objects they had taught in the current session and any of the previous sessions. So for this study, we developed a continual learning system in which users could teach the robot through a graphical user interface loaded on a tablet. So users could start a teaching session, show the robot different images of the object, and label it. And then the robot would train the continual learning model on the object data and the label provided by the user. Users could also use the GUI to test the robot, and in that the robot would use the continual learning model to find the object specified by the user on the table, and then use the arm to point to that object. So we conducted a between subject study in which participants interacted with 2 different continual learning models. So one was fine-tuning, and another one was CBCL, which is a state-of-the-art continual learning approach. And the main difference between the 2 approaches is that fine-tuning suffers from this problem of catastrophic forgetting, in which the model forgets the previously learned knowledge whenever it learns something new. And CBCL is designed to deal with this problem. So in this study, we focused on answering 4 research questions. Our first question was to understand how human users label objects when teaching a continual learning robot over multiple sessions. So we noticed that there were significant variations in object labeling strategies between the users. Particularly, we saw that there were as high as 14 different labels given to a single object between 40 participants. And these labeling strategies varied from very generic to very specific labels. So for example, generic labels could be apple, banana, or specific labels could be red toy apple. We also noticed some unique labeling strategies. So for example, some participants gave the same label to multiple different objects, and then some participants gave multiple labels to a single object in their interaction with the robot. So our next 3 research questions focus on understanding if the continual learning robot's performance affect the way users teach over multiple sessions, and if the teaching style changes over multiple sessions, and if there's a difference between teaching style and performance of the robot between expert and non-expert users. And we define experts as participants with prior robot programming experience. So for this, we conducted a 3-way ANOVA with independent variables being session number, continual learning model, and previous programming experience of the participants, and dependent variables being the classification accuracy of the models, and then teaching style of the users determined in terms of the number of images shown per object, the number of teaching phases they started in each session, and if users retaught misclassified objects. So for example, if they taught the robot, they tested the robot, and then the robot misclassified, they went back to reteach different misclassified objects by the robot. So in terms of classification accuracy, we saw that it was overall very low compared to when these models were tested on static object datasets. And we did see that it was affected for the fine-tuning model However, we didn't see any significant difference in accuracy for experts and non-experts for both conditions. So for a number of images per object, we saw that the overall number was very low, which shows the feasibility of continual learning robots to learn quickly and with low data in real-world environments. We didn't see any significant difference between experts and non-experts for CBCL, but experts did show higher number of images in the FT condition. Specifically, we noticed that higher number of images were shown by experts in the later sessions, and we think it's because that the performance of the robot dropped in later sessions, specifically for fine-tuning, and then experts compensated for that by teaching the robot even further. Finally, in terms of teaching phases and reteaching misclassified objects, we didn't see any significant ANOVAs. However, we did notice that 50% of the participants started more than one teaching phase per session, and 45% of the participants retaught at least one misclassified object to the robot, which is very interesting and shows that participants were motivated to improve the performance of this robot that could be deployed in their own household environments. So going back to the research questions, yes, we did notice that users' teaching styles are affected by the continual learning robot's performance, and they evolve over multiple sessions. We also noticed a difference between the teaching styles of experts and non-experts, but the performance of the robot was not significantly different between experts and non-experts. So in conclusion, in this paper, we took a human-centered approach to continual learning to understand how users interact with and teach continual learning robots over repeated interactions. And our results indicate significant variations in the teaching styles of the participants over repeated interactions with the continual learning robot. And unlike static continual learning test setups, we noticed that the teaching process and the data might be dynamic over multiple sessions when the robots are deployed in the real world. So future research should focus on developing continual learning models that adapt to the teaching styles of their users. Thank you. And if you have any questions, please let me know.